Hello and welcome to lecture number 37, which is a continuation of the previous lecture where we have been discussing about the variational theorem and about the trial function. So as we knew that if we choose a trial function and if our guess is reasonable enough, so we get an energy value which is close to the ground state energy. So depending on our guess, we can find a good enough energy value. Now the thing is, today we will see that how to choose a trial function for best result. So that means, is there any systematic way to guess a trial function? So before we begin, let's take an example. So I'm talking about the free particle in a one-dimensional box, and we have already solved the case. So there, if you remember, while discussing that chapter, I told you that if we take the trial function phi as this or this, okay, so x multiplied by a minus x or x to the power n multiplied by a minus x to the power n, it actually satisfies the same boundary conditions. So what are the boundary conditions? So the boundary conditions were that at x is equal to 0, phi should vanish, and at x is equal to a, the phi should vanish as well. Now we can see by guessing this phi, it satisfies both the boundary conditions. So it can be an acceptable, well-behaved function for a free particle in 1D box. Now the thing is, if we guess that phi is a linear combination of these two functions, that is c1x multiplied by a minus x plus c2x squared multiplied by a minus x whole square, then with all our desired calculation, if we do it correctly, we will find the energy minimum. That means the energy that we are going to find out by applying variational theorem would come down to 0.1250028 square by m square. Now remember, we are talking about energy minimum. That already means that we are talking about ground state where n is equal to 1. Can we compare that with the E minimum actual or the E minimum exact? If you remember, for n is equal to 1, this value should be 0.1250008 square divided by m square. So now you see how close we get compared to this and this in these two values. Okay, so therefore it suggests that by using this phi, okay, as a linear combination of these two functions, probably we can end up with a very good result. So this gives us a premise to choose or to guess a trial function that would give us a best result. Okay, so now we are going to write an expression that would give a systematic way to find a trial function. So now let's erase this part and do it here. Okay, so what's the systematic way of guessing a trial function? From the example that we just took a look at, from that now we can guess that we can take a summation or basically a linear combination of some suitable or well-behaved acceptable wave functions. Okay, so here the trial function must be a summation of C and Fn's. So C is the variational parameter that we are going to optimize, and we can take a number of functions like that. Okay, so here in this particular case today, we take an example, and the example is that we take up to two functions, n is equal to 2. So therefore, our phi becomes c1 f1 plus c2 f2. Okay, clear? And then also we assume that both C or C1 and C2 and also F1 and F2 are real. Okay, so therefore we now start to find our variational expression. So we are going to find this one. E phi is equal to phi star H phi delta divided by phi star phi delta. So this is our goal, to evaluate the energy. So energy minimum. So now our phi is this. Okay. So therefore we have to individually evaluate this one and this one. Okay. And then we have to optimize both C1 and C2. Once we optimize both C1 and C2, we can be able to find E phi. So that's our goal today. So let's start. So we start with this one, phi star H phi delta. So now we can take a look that phi star H phi delta in this case is equal to, remember, simply phi H phi delta. Why? Because our both C1, since both C1, C2, F1, F2 are real, so that means phi star is equal to phi. So instead of writing phi star, I can now directly write phi, because phi is equal to phi star is equal to, so we have now C1 F1 plus C2 F2 multiplied on H operator of getting operated on C1 F1 plus C2 F2 d tau. Okay, so and we have the integration sign, of course. Okay, so now if we expand this term, okay, we will get several of the terms. Okay, so now before going into that, I want to express whatever the terms that we derive here in terms of matrix elements. So this is a new terminology or a new way of representation that we have not talked it before. So I want to write something like this. So if I write like something F1 H F2 d tau, so this I can represent as, or this is represented as H12. Okay, so if or rather it is represented as Hij. Okay, so where I and j can be different, or I equal to j. And similarly here I can write that F1 F2 d tau. Okay, we can represent it by S12, or rather Sij. Okay, so I could be equal to j, or I may not be equal to j. So these terms, H12 or S12, are known as matrix element. So I haven't talked about this matrix element in detail. It's because if we talk about the Dirac notations, then these matrix elements become more relevant. So we are not going into those details. So, but for the time being, let's recognize H12 and S12, or H11 or S11. So if we can further expand it, so what we are going to get is C1 square H11 plus, we are going to get C1 C2 C1 C1 square H11, and then we get C1 C2 H12. Then again we get plus C1 C2 H21. Okay, and plus we get C2 square H22. Okay, isn't so? Now here I would like to draw your attention that if we look about the expression of H12 and H21, okay, so this is H12, and one of our underlying assumption that F1 and F2 not only real, these are quantum mechanical, about H, okay, yeah, so the H operator, Hamiltonian operator, this is a quantum mechanical operator, valid quantum mechanical operator, so that means H is Hermitian. And since both F1 and F2 are real, so that means we can write that H12 is equal to H21 because H is an Hermitian operator. So if we apply the condition for the Hermitian one, uh, this equality is automatically implied, okay, because these are all real, F1 and F2. So F1 star is equal to F1, F2 star is equal to F2. So we can actually write like this, and therefore it reduces to C1 square H11 plus 2C1 C2 H12 plus C2 square H22. Okay, so this is the expression of this part. So similarly, we can try to obtain the expression for phi star phi d tau. Okay, yeah, and so remember, definitely this is not 1 because this is not normalized and we don't know what it is. And similarly, if we try to expand this, okay, so it will automatically go into the phi square d tau integral. And as we have defined our elements of integration, the matrix elements like this, Sij or Sgi, whatever. So now we can write the same thing as C1 square S11 plus 2 C1 C2 S12 plus C2 square S22. So here we have implied one more relationship, that is Sij is equal to Sji. Okay, so it doesn't matter because here F1 and F2 are real, so it doesn't matter in which order we are multiplying, F1 multiplied by F2 or F2 multiplied by F1. So these means identical ones. So therefore we got these two expressions, that one is this and another is this. And so therefore the variational theorem wants us to take the ratio of this divided by this. So we are going to take the ratio this divided by this, and the ratio, so if we simply take the ratio over here, okay, this divided by this would be is equal to the energy, variational energy, and which is dependent on phi. So this should be E phi, the upper bound of the ground state energy of the system. Okay, so now definitely I have to clean the board and I will start with this equation over here. Okay, so let's do it. So therefore, in continuation, I have written this equation. Okay, so what we have found out, the expression by assuming phi is equal to C1 F1 plus C2 F2. So here now we see that the energy has to be minimized with respect to C1 and C2, and then we have to solve for C1 and C2. So minimization of energy with respect to C1 and C2 means basically we have to find out these two partial derivatives, that is del E with respect to means energy with respect to C1, partial derivative del E del C1 at C2 constant, and we have to set that is equal to 0, and also del E del C2 at C1 constant, we have to set this thing is equal to 0. So basically from here we are going to find out two simultaneous equations. Okay, so we have to frame those equations. So therefore I have written the above equation, and by multiplying E with this is equal to this. And I have not written H cap every time because to avoid repetitive symbols. So let's make it to make it simple. I have used only H. Okay. So therefore we have this expression now. Okay. So what I'm going to do is I'm going to take the derivative of the entire equation with respect to C1 by taking C2 constant. And then therefore, and at the end we have to set this thing is equal to 0 in order to minimize minimize energy with respect to C1. So therefore, let's do it. So what we get is we first take the derivative of this, okay, with respect to C1. So it becomes 2C1 S11 plus 2C2 S12 plus C2 square S22 multiplied by again del E. So we can take del E del C1, okay, at C2 constant. So we will now assume that C2s are constant. So again 2C1H11 plus 2C2H12 plus C2 square H22. Yeah. Actually, I have made a mistake here. I have made a mistake in taking the derivation of this. The reason because that whenever I have derived that, then the energy should be here, E, okay? And plus we can have del E del C1 multiplied by these entire things would be constant now, okay? So pardon for this mistake, sorry about that. So yeah, so this is okay now. So this is the product, and once we are taking the derivative of it. So by taking E fixed, we have taken the derivation of this with respect to C1, and then again by keeping this part fixed, we have taken the derivation of E with respect to C1 is equal to this. Okay, so no problem with that part. Okay, so now what happens is that we can write here now. We would deliberately set del C1 C2 is equal to 0. So if we set that part is equal to 0, so therefore this entire part would become 0, or we can write that 2C1 S11 plus 2C2 S12 plus C2 square S22 E, okay, is equal to, we have 2C1 H11 plus 2C2 H12 plus C2 square H22. Okay, so now what happens is the question is can we now further simplify it? Okay, so what you're gonna do is now from this equation, okay, we have to look whether we can simplify this equation a bit further. Okay, so let's erase this part, and we start this equation from over here. Okay, so before we proceed, there was one more mistake while taking the derivative. So if we see here that this part C2 square S22 is constant part, and here also this is the constant part. So or here, when we take the first derivative, actually this part should vanish. So we have here 2C1 square, it comes to 2C1, we have 2C1 C2, it comes to 2C2, because we are taking the derivation with respect to C1, and with respect to C1 here everything is constant. Okay, so this part would not appear here. So therefore the equation should be like this on the left hand side, and on the right hand side also this part should not be appearing, because this is 0. Okay, so now this plus this, so here also this part should not okay, no, here it is sorry, so here it is the constant part anyway. So now once del C1 is equal to 0, so this part becomes 0. So we have finally this equation now is equal to this. Okay, so now we have to simplify this thing further. How we can simplify this further? Look, we have 2 in all sides, so therefore it simplifies into something like this, is equal to C1H11 plus C2H12. Okay, so now what I'm going to do is I'm going to take the C1 terms at one side and C2 parts at the another side. So why am I doing that? It will be clear to you soon. So therefore I want to take C1, and then I have within bracket H11 minus it would come to ES11 plus again C2 within bracket H12 minus SES12 is equal to 0. Okay, so therefore here I have one equation, okay, that I got by setting del E del C1 is equal to 0. But remember, we have two unknowns, C1 and C2. We have to solve this. So therefore, this is one equation. We have to find another simultaneous equation from this relationship del E del C2 is equal to 0. So by setting del E del C2 is equal to 0, we have to find another equation like this from this. So the question is, how can we find that? So if we do the same treatment, we will find another equation which we can easily guess. So if we do our things correctly, so what we will end up with is we will get something like this. Okay, so it's better I erase this board and write the two equations freshly over there. It will make sense. Okay, so now as you can see, I have just rewritten this equation at the bottom over here, and it obtained from del E del C1 is equal to 0 by setting this condition. And if we apply the next set of condition, that is del E del C2 is equal to 0 and C1 is constant, we should expect to get this expression. Okay, H12 minus ES12 plus C2 multiplied by H22 minus ES22. That should be is equal to 0. Now the thing is, these are the two simultaneous equations, and we can call it equation 1 and equation 2. So we should be able to find the values of C1 and C2 by solving this. The question is how to solve them sensibly. So one option is there should always exist a trivial solution. Okay, So the trivial solution is definitely C1 is equal to C2 is equal to 0. Okay, but we are not interested in the trivial solution. We are interested into the non-trivial solution. So how to find the non-trivial solution? So to find the non-trivial solution, so according to the knowledge from algebra, what we can say that the determinant, okay, obtained from these two set of simultaneous equation. So I'm writing the determinant over here. So this is a 2 cross 2 determinant. Okay. So this 2 cross 2 determinant must be 0. So it would form a quadratic equation. So we can write, so this is a 2 cross 2 determinant. Okay. And this would give a quadratic equation. Okay. So now you see these are free from, so the quadratic equation that we will get is free from C1 and C2 terms, definitely. So in order to find C1, C2, what we have to do, we have to find E first, the energy. So therefore, we can only find energy by solving this determinant. And the condition is, you can only get a non-trivial solution where this 2 cross 2 determinant must be equal to 0. And from this we'll get a quadratic equation, obviously. So if we solve the quadratic equation, so this quadratic equation would have 2 roots. So you will have the solution as 2 roots. Okay. So what we have to take, so we have to take the minimum value because we are minimizing the energy. So out of the 2 roots, whichever value is the lower, the smallest, we have to take the smallest value as the energy. So the smallest energy value would give nothing but E5. Okay. So once again, so the smallest value that would give you our desired energy E5. Okay. Or means the minimum energy, which is the upper bound of the ground state energy. Now once we find the energy E value, then we can separately plug in those values of E because H11, S11, those are known, those can be known from the integration. So we can plug in those values of E over here in these equations and we can individually find C1 and C2. Okay. So this is the general process how we can find the energy from variational method, and and this process involves the optimization of the parameters, variational parameters C1 and C2, and the determinant that we come across here. Okay. So this kind of determinant is known as secular determinant. Okay. So from now on, as we would go across into the other chapters like atoms and subsequent quantum mechanical chapters in future, we will come across this secular determinant term very frequently. Okay. And from the secular determinant, once we have the quadratic equation, okay, so that quadratic equation is also called the secular equation. So a secular determinant gives you a secular equation. Solving a secular equation, you will have two values as the square root of something, and from those two values we have to always choose the lesser of the values, which would give us the energy minimum. Okay, so the ground state energy that we are looking from the variational method. So I have now explained the whole process. So how to systematically choose a trial function. So remember, we have chosen the trial function as a linear combination of some acceptable wave function like C1 F1 plus C2 F2, and more importantly, that if we choose something like this as a trial function, that phi is equal to n Cn Fn. Okay, so instead of 2 cross 2 determinant, we have n by n determinant. Okay, because we have n numbers. So how to solve this an n by n determinant? So we know that a 2 by 2 determinant can be solved by framing the quadratic equation, and from which, if the quadratic equation can be readily solved, we can get the square root. If it is not readily solved, we can employ the method by Sridhar Acharya, where we can get the roots, okay, acceptable roots. But if we get an n by n determinant, then how to solve the equation involving how to handle the secular equation? Because we can identify the secular determinant, no problem. Then we have to take the help of computer programming to find out, to solve the secular equation framed from the secular determinant. Okay, so this is how we actually approach. So I guess today we will stop it here. So we have one more lecture on the variational method that we have to deal with. That is, we have to take one or two simple examples on how to use these the process of secular determinant and the secular equation. Okay, so in the next lecture, that will be our last lecture from this approximation method chapter. So there we will deal with one or two regular examples involving secular determinant. So I will see you in the next lecture. Till then, goodbye.